In this video, I'm going to discuss a method for calculating the hydraulic thrust on curved surfaces. In the discussion that follows, I'm going to assume some familiarity with calculating the hydraulic thrust on plane surfaces. Let us consider the thrust on a curved surface due to a fluid with which it's in contact. First, we note that we have a hydrostatic pressure distribution, which means that the pressure at a point on the surface is proportional to the vertical distance from that point to the fluid surface. We also know that the direction of the hydrostatic pressure is perpendicular to the surface from the fluid towards the surface. This means that if we look at a point on the curved surface at a distance h below the fluid surface, we have a pressure perpendicular to the surface with magnitude ρgh pascals. If we are to find the thrust on this curved surface, we need to integrate the pressure over the surface. In general, analytical integration is difficult. Here, I'm going to present an alternative approach in which the horizontal and vertical components of thrust are determined separately. The total hydraulic thrust is then determined by a vector summation of the horizontal and vertical components. Let's consider a curved surface which is part of a wall submerged in a fluid. We are going to examine the thrust only on the curved part of the wall, which is the red area highlighted here. Although the analysis that follows does generalize, we are only going to use this method for cases where the shape is uniform in the z direction, and we perform our analysis in the xy plane. Consider an elementary surface dA, which is h meters below the fluid surface. We want to calculate the hydraulic thrust on this elementary surface. I'll denote the force on the elementary surface as dF. We know that the pressure at this depth is ρgh, so the magnitude of dF will be ρgh times dA. We also know that this force will be normal to the surface. If dA is at an angle theta to the vertical, then dF will be at an angle theta to the horizontal, as shown here. The components of dF in the horizontal and vertical directions will be cos theta times dF and sin theta times dF respectively. Now we can integrate each of these over the surface separately to find the components of the hydraulic thrust. Looking at the horizontal component first, we have Fx equals the integral of our elemental force over the area. Rho and g are constant, so we have simply ρg times the integral over the area A of h cos theta dA. Let's look at this integral. Cos theta dA is the projection of our elemental area onto a vertical elemental area as shown here. The integral thus generates a projection of our curved surface onto an imaginary vertical surface, illustrated here as a purple line. And the integral is equal to the pressure head at the centre of gravity of the projected imaginary surface times the area of that surface. In the case of a curved surface which is uniform in the z direction, the projected surface is rectangular and has the same height as the curved surface. Now, since ρgh bar is the pressure at the centre of gravity of the projected surface, Fx is equal to the force that would act on the projected surface. This makes the calculation of the horizontal component of thrust very easy. We don't have to repeat the integration, we simply project our curve onto a vertical surface and calculate the thrust on that surface. This also means that we can use the pressure prism method, since we know that the volume of the pressure prism is equal to the hydraulic thrust on the imaginary surface. This has the added advantage that it also tells us about the line of application of the force, since this goes through the centre of gravity of the pressure prism. Let's look now at the vertical thrust. We established earlier that a thrust of ρgh sin theta dA is exerted on our elemental area dA. Integrating this over the curved surface, we get rho g times the integral over A of h sine theta dA. Looking at this integral, we have the projection of dA onto a horizontal elemental area sine theta dA, and the integral is simply the volume of fluid contained in the prism fluid above the curved surface. The vertical thrust is thus the weight of the fluid in this prism of fluid. The line of application of the thrust is through the centre of gravity of this prism of fluid. The direction of the vertical thrust depends on the nature of this prism. If it is a real prism, i.e. the fluid is above the surface we are interested in, as shown here, then we have a downward thrust. In the case where the fluid is below the surface, the integral is the same. But in this case, the magnitude of the vertical thrust equals the weight of the fluid that would fill the space above the surface, i.e. instead of a real prism of fluid, we have a virtual prism of fluid. The thrust in this case acts upward through the centre of gravity of the virtual prism of fluid. The total thrust is simply the vector sum of the two components. Thus the magnitude is the square root of fx squared plus fy squared, and the angle of incidence is arctan fy over fx. Okay, let's look at an example. In this example, we want to determine the thrust acting on the radial gate shown here. Consider the horizontal component of the thrust. First, we project our curved surface onto a vertical surface. The centre of gravity of that surface will be at a distance a half r from the surface, and the area of the surface has height r and width 1 metre, because the question states a unit width. Thus, the horizontal component of the force is rho g times a half r times 1. Alternatively, we could use a pressure prism, which has a base length rho g r, height r and width 1, generating a volume of a half rho g r squared, which of course gives us the same result. Taking the density of water to be 1000 kilograms per metre cubed, an acceleration due to gravity is 9.81 metres per second squared, we have 19,620 newtons. The line of action of the horizontal component of force is the centre of gravity of the pressure diagram, which is 2/3 r from the water surface since it's a triangle. Thus y bar is 4/3 of a metre. Moving on to the vertical component of thrust, we know that it is an upthrust, and its magnitude is equal to the weight of the water in the virtual prism above the gate. In this case, we have a quarter circle and a width of 1, giving us rho g times a quarter pi r squared times 1. This comes to 30,819 newtons. To find the line of action of the vertical component of thrust, we need the centre of gravity of a quarter circle, which is 4r over 3 pi, giving us 0.85 metres. Finally, we calculate the magnitude of the total thrust on the gate, which is 36,534 newtons, or 36.5 kilonewtons, and the angle to the horizontal, which is 57 degrees and 31 minutes. In part 2 of this video, I will look at some more examples of how to apply this method.